Proof systems are interactive protocols in originating from theoretical computer science, where you have a party called a prover and demonstrates some statement to a verifier that the verifier somehow can't verify on their own.
Proof-of-replication is a proof of space, and in its purest form, we have a prover and a verifier, and the prover wants to prove that they're storing some data that they committed to store. And the verifier challenges the prover to ensure that the prover has been correctly replicated some data.
You can think of it as a useful proof of space. It's a proof that I'm not only using my disk to store space or just any junk data, but that I'm actually using it to store a particular file of interest. And so this kind of ties together this thing called a proof of retrievability, which is a proof that you actually have in your possession a certain file that the verifier is aware of, and a proof of space. And so a proof of replication is kind of at the same time a proof of retrievability for a particular file, or it can be, and also a proof of space.
So in a high level, the protocol works in this particular way. The prover commits to store some data and runs an encoding on this data. The encoding is meant to be slow because in a later point, the verifier will be challenging the prover. If the prover is able to respond quickly, it means that they've done the encoding. If the prover doesn't reply quickly, they're able to generate some data on the spot and lie about the storage that they have.
Proofs of replication are a critical component for the Filecoin network. It's the main algorithm that the network uses to make sure that miners are behaving correctly, that they are indeed storing the data that they promise to store for clients. In a way, proof of replication is the heart of Filecoin in the same way that proof of work is the heart of Bitcoin.
Filecoin is using it in sort of an extra interesting way, because proof of replication is not just a proof, again, of retrievability, it's a proof of space. It's a proof of useful space. And Filecoin, like Bitcoin or Ethereum, is a decentralized network with a ledger, and it uses a Sybil resistance mechanism. Like proof of work in Bitcoin, Filecoin uses proof of space. But while Bitcoin's proof of work just kind of wastes energy, Filecoin's proof of space is a byproduct of the system actually storing files.
Recently, we've had a tremendous amount of progress improving the performance and security guarantees of proofs of replication.
In proof of replication, we went through a pipeline from research to development. At the very beginning, we had a technical paper, which is what we released in 2017. And since then, we've done a series of improvements.
Constructing a proof of replication was a very tricky task. Remember, the key difficult thing to achieve with the proof of replication is this verifiable proof that you're using space to store a particular file, okay? And we want to achieve this in a cryptographic sense, right? And sort of the best possible thing that you can do, kind of, is basically achieve what's called a tight proof of space. And it's basically a proof of space where you really can't save anything, okay? And so if you're producing a proof of space where you really can't save anything, then you might as well store a movie file, right? And then on top of that, you can give a proof of retrievability of a particular movie file to users. But from the perspective of the proof of space verifiers, they know that you can't save anything, so you might as well use a space to store what you're claiming to store. And so that's sort of the property you wanted to achieve. And it actually took us a while to iterate and make these proofs of space tighter and tighter and tighter until we got to something which really had the security property that we wanted. So it started with kind of just a basic proof of space based on this graph thing called a depth robust graph. And it's a tool that's been used a lot in computer science, but we were using it to construct basic proofs of space. And then they weren't quite tight enough, right? So the adversary who might, save, a small percentage of the data, or actually even half of the data, and that wasn't good enough for us, and therefore we were improving on it. And then we got to kind of combining it with these other things called expander graphs, which have also been used for proofs of space. So we took these two different techniques that were being used to construct proofs of space that weren't really good enough, and we sort of combined them together in an interesting way and ended up with something which was the tightest proof of space that ever existed. And so it was not only necessary for Filecoin, but it was a contribution to the entire literature of proof of space, since it's the tightest proof of space that there is, and it was actually necessary for Filecoin's application. Any tight proof of space can be used to build a proof of replication with inefficient unsealing, okay? Inefficient data extraction. Fast unsealing is harder to achieve, and that's what we achieved with Zigzag, which is not just a tight proof of space, but a tight proof of space with fast data extraction, where you're using the proof of space to incentivize file storage, and you want to make sure that whoever produces this proof of space will be using it to store files of interest. Then you need to guarantee that there's no reason that the adversary would do something else that would destroy the file storage format and therefore lose the data and gain an advantage in passing the protocol. And so that's where you really need Zigzag. You need it to be as tight as possible so that you know there's no cost savings for not following the honest protocol, and then the honest protocol is the only way to ensure retrievability or lossless encoding. And so that's why Zigzag is most appropriate for that setting.
This proof of replication is the current proof of replication that we've been developing.